Hi everyone. My name is İlker from Atatürk University's Department of Environmental Engineering. Today I'm gonna present my research on an important environmental challenge on hexavalent chromium removal using modified zeolites. Before we dive into the details, let me outline what we will cover today. First, we will discuss the introduction and problem statement. After that, we will explain our material and methods, and we will continue with the effect of modification type and then explaining optimization results. Fifth, we will explain the absorption mechanism, and finally, we will conclude with the conclusion. Let me start with why this research matters. Hexavalent chromium is highly toxic and carcinogenic. It releases from major industrial sources like electroplating, leather tanning, textile dyeing, and pigment manufacturing industries. So what makes chromium-6 particularly dangerous is that it's highly soluble and mobile in aqueous environments. Unlike some pollutants that settle, chromium-6 remains dissolved and readily contaminates drinking water sources. It's very dangerous and a cancer hazard. Adsorption is recognized as an effective, low-cost, and environmentally friendly technique for removing such pollutants. Natural zeolites are promising. They work well for cationic pollutant, but here's the problem. They show limited affinity for ionic species like chromate and dichromate ions, meaning anions. That's where surface modification comes in. Using surfactants or metal oxides, we can enhance the anion exchange capacity of zeolites, making them far more effective. Then we will continue with material and methods, our experimental approach. We took raw zeolite and modified it using two distinct strategies. First, salt modification with calcium chloride, magnesium chloride, hexahydrate, and ammonium chloride. This coded CMZ, MMZ, and NMZ. Second one is surfactant modification with stop cetyl trimethylammonium bromide, creating what we call SMZ. Our methodology involved batch tests using a constant solution volume of 100 millimeters conducted at 25 degrees Celsius with 200 RPM stirring. We use synthetic wastewater with potassium dichromate as our chromium-6 source. We measured chromium concentration directly using UV-Vis spectrophotometry at 350 nanometer. Our evaluation criteria is removal efficiency, which is calculated from the initial and final chromium concentrations in the solution. Now let's compare how different modification approaches performed. These experiments were conducted under identical conditions: initial chromium concentration of 50 milligram per liter, absorbent dosage of 5 gram per liter, contact time of 24 hours, and natural pH conditions. Here are the striking results. Raw zeolite only showed 0.13% removal, which means essentially ineffective. Salt-modified samples, zeolites, performed better, ranging from 2.47 to 16.05% removal, but the surfactant modified zeolite, our SMZ sample, achieved almost 30% removal. This was dramatically superior, more than 200 times than raw zeolites, and significantly better than any salt-modified variant. Next, we optimize operating parameters for SMZ. First parameter is contact time. You see the experimental conditions, initial chromium-6 concentration, 25 milligram per liter, SMZ dosage of 10 gram per liter. Natural pH, it's about 5.5. What we found was very telling. In the first 15 minutes, alone, we achieved about 83% removal efficiency, rapid initial adsorption, extending the contact time to 120 minutes. We obtained more than 94% removal efficiency. That's a 11-point improvement. At 240 and 480 minutes, we saw only essentially no significant additional removal. The second parameter we optimized was SMZ dosage. Here are the experimental conditions. Again, we used 25 milligram per liter. Optimum time 120 minutes, and we use also natural pH. The dosage tests revealed clearer pattern at the lowest dosage of at dosage of 2.5, we achieved 36.55%. As we increased the dosage, we saw an almost steady rise up to 86.62% removal. Dosage for 4.5 gram per liter. This makes sense. More adsorbent means more available binding size. However, the improvement rate slowed considerably beyond 7.5 gram per liter. At our optimum dosage of 10 gram per liter, we achieved 94.72% removal. This represents the practical sweet spot. Going beyond that offers minimal additional benefit while increasing cost and operational complexity without proportional gains. The third one is initial pH. Again, we use 25 milligram per liter chromium-6. Optimum time is 120 minutes. Optimum SMZ dosage was obtained as 10 gram per liter. As you see from the figure, pH had a profound effect. The maximum removal efficiency was obtained at pH 5 as 96%. This is our headline results. What you see is a strong pH dependence directly related to both the surface charge of the SMZ and how chromium speciation changes with pH. Below pH 5, efficiency declined slowly, as you see, but above pH 5, it declined much more dramatically. This makes excellent sense as acidic pH around 5. Stop-coated zeolite surface maintains strong positive charge, and the dominant chromium species is monovalent chromate ion. This creates maximum electrostatic attraction. As pH increases, hydroxide ions compete for binding sites. the surface becomes less positive and the dominant chromium species shift to divalent chromate form, which repels from the increasingly neutral surface, hence the dramatic efficiency loss at higher pH. Now let me explain the mechanism driving these remarkable results. Adsorption primarily occurs through electrostatic attraction forces between the positive bilayer surface created by stop and the negative charge of chromium-6 ions, as you see from the figure. At our optimum pH of 5, the dominant chromium species is monovalent hydrogen chromate ion. When pH increases, several unfavorable things happen simultaneously. This is why acidic conditions, specifically pH 5, are essential for maximum performance. In conclusion, first of all, stop-modified zeolite is highly effective for chromium-6 removal. This is not a marginal improvement, it's a transformative modification. Second, we achieved about 96% removal efficiency achieved at optimal conditions, contact time of 120 minutes, SMZ dosage of 10 grams per liter, and a pH of 5. The third one is the essential acidic pH is essential for maximum performance. This is very crucial for practical implementation. The fourth one is that this represents a cost-effective alternative for industrial wastewater treatment. Thank you for your attention. If you have any question, I will be glad to answer them.